Today she's going to talk actually about two different projects. The first, she was an intern over the summer at a consulting firm, and so she's going to share a little bit about what she learned there. And then this spring semester, she's actually been working on our campus in the Statistical Consulting Center with Dr. Bergen. And so she's going to share a little bit about one of the projects that she worked with in the Consulting Center as well. So she is going to graduate here in a couple weeks with a bachelor's degree in statistics, and we're excited to hear her share everything with us today.
All right, so here is my capstone experience, first on my analysis programmer internship from over the summer, and also the consulting project through the Winona YMCA membership project. So first, my analysis programmer internship, this was over the summer with Vandenhouten Research Services. My dad actually owns the company. So that was a fun bonding experience. And they serve as a consultant to the pharmaceutical research industry. So just some of the primary tasks. First, we write programs in SAS, or statistical analysis software. And using SAS, we produce data sets, tables, figures, and listings, and then also verify correctness via double programming. And I'll go more into that in a little bit. And then we also just provided data management support for the clinical research process. So the main goal of this internship was to learn the process of how a large-scale statistical team operates. So although I did write a lot of SAS programs, this presentation will focus on the process rather than the code, just because all of the drug studies I was involved with are confidential. So first, just going over what the stages are of a clinical trial. You'll have phase 1, which studies the safety of the treatment, and that is often less than 100 participants. Next is phase 2, which studies the efficacy, and this lasts up to 2 years with a couple hundred participants. And then phase 3, which studies the safety, efficacy, and dosing of the treatment, lasting 1 to 4 years with a couple thousand participants. And then last is phase 4, which studies the long-term effectiveness, cost, and other uses for the treatment. And this lasts a long time with thousands of participants. So most of the studies I was involved with were phase 3, so a couple thousand participants. And the contractor I worked with has been involved with a study as small as 8 participants, but also up to 10,000. So you can get quite a range. So next we'll just talk about the stages of the data. So first you have the raw data, which comes from the patient's healthcare provider. They just enter it in an electronic database. And then next is the study data tabulation model, or the SDTM. And finally, you have the analysis data model, or the analysis, or the ADAM data sets. So just going into the SDTM, there are format requirement guidelines from the FDA to ensure consistency across the different studies. And there are several SDTM data sets within each study. So subject demographics, adverse events, and laboratory results, just to name a few of them. And this data set is used for simple summaries and listings. And then next you have the ADAM data sets. So these are derived from the SCTM data sets, and they are required if there are any calculations with the data. So not every study needs to have the ADAM data set, but if there's any calculation, then you are required to have them. So here's just a little look at an SDTM lab results data frame. So this is for different chemistry listings, and here are the lab measurements. So that's just a look at it. And then here is the corresponding ADAM data set, so the analysis data set for the lab results. This is just for one participant. So here, that's a flag. The Y is a flag saying this is the baseline value. So that's the screening. And then here, that's the baseline column used as a reference. And then this is a post-baseline flag. So this is just saying, yes, this is a measurement taken after the baseline. And then here is the lab at each visit. And then finally, here's just one of the simple calculations. This is just a change in baseline. So that's just showing you use the base column as a reference and then to calculate the change. So next we'll go into the programming team a little bit. So it's headed by the lead programmer, and this person will oversee the production and validation of all of the outputs in the study. The lead programmer can also do production and validation, but it's usually not the best idea just because they need to be available to answer questions. So they also check the output status of each of the outputs and document all communication between the programming team members. And they also help facilitate conversations and questions between the programming team and the study statisticians and data management team. And then finally, when the study is completed, they archive all of the necessary files. So that includes programs, outputs, and all of the communication between team members. So next you have the analysis programmers. These programmers will follow the statistical analysis plan, or the SAP, for guidance on any table, figure, or listing specifications, and then also deliver the production and validation of an output. So I was an analysis program intern, so I was part of this team, and I worked directly with one contractor. And the programming teams I was involved with had about 8 analysis programmers. So just to give you an idea of the team I was a part of. So next, creating output. You follow the clinical study report, and there are many requirements on what is to be included in that final delivery. The programming team will be assigned to either the production or the validation of the outputs, and the lead programmer will assign you to these. And sometimes the validation is done via double programming. So that is when both the production and validation are written in separate SAS programs, and then they compare to make sure they match. And sometimes clients choose not to do double programming validation just because it, 1, costs more, and 2, takes a lot more time. So sometimes if they have a really tight timeline, they just need to get it done. So then the validation programmer, instead of writing a separate SAS program, will just review the both the program and the output for different errors and omissions. And then they'll also compare the final output with the shell in the statistical analysis plan. So just some of the results. First, we'll talk about listings. So all of the data collected throughout the clinical trial is required to be listed in the final clinical study report. So just as an example, every blood pressure measurement for every subject at every visit must be listed. So when you have 10,000 participants, you're gonna have thousands of pages. So it's just really important to automate the process and have a uniform format just to have consistency across that. So then summary tables. Each of the summary tables will have a table shell in the statistical analysis plan. So this is just an example of a subject demographics table. So they just have the empty columns, and then you obviously fill them with your program. And then some clients will also provide variable names within the table shell just to make programming go a little faster. So here, using that code, you would use the Atom data set, so ADSL, and then the age variable in there. So that just helps programming go a lot quicker, so you don't have to look through pages of variables. So then we'll talk about a figure. This is a change from baseline figure, which studies the safety of a drug, because it's really important to know after you give the drug that the labs don't go crazy, because that's obviously not safe. So here on the x-axis, you have the visit. Then on the y, you have the change from baseline. And then that 0 reference line is just saying if there's no change from that initial value, then it will be 0. And then just here's an example. At week 3, the visit at week 3, there are 493 subjects in the experimental treatment group in red, and 253 in the placebo blue group. So that just compares the 2 treatments. And then finally, just in conclusion for this internship, the most important takeaways from this internship were the importance of data analysis, efficient programming, and effective communication among team members. and also the importance of a uniform and automated process. When you're dealing with data sets that are tens of thousands of rows, it's just really important to kind of know where you're at. And then also just see real life applications of what we've been learning the past 4 years was really cool. However, there were some limitations. So first, I had very limited SAS knowledge going in, and I still am learning a ton. So just would have been nice to know a little bit more before I was kind of thrown in there. And I also wish I saw more of what the statistician's role includes. I was mainly doing that programming in SAS. And then next, we're just going to switch gears a little bit to my Winona YMCA membership project. So as Tisha said, I've been doing consulting work with Dr. Bergen in the Statistical Consulting Center on campus. And this was a separate client outside of the campus. So first, the client's research questions. How does Winona's YMCA membership compare to other YMCAs located in counties of similar size? And also, what will Winona's membership look like in the next few years? So first, we wanted to compare counties. So Winona's county population is about 49,000, and we considered counties with a population anywhere from 20 up to 80,000. So here is a comparison of all of the YMCAs we gathered data from, and you have the membership over time, and a lot of them have a huge drop, and that is in 2020 due to COVID. And since that was such a weird year, here is separate graphs excluding that huge drop in 2020. So most locations did have a decrease in membership prior to COVID in 2020. But if you look at Winona in blue, the membership remained about steady and then had a large increase in 2021, and they opened a new location if you didn't know. So then just to compare these counties a little bit more, we looked at some census data from the locations, and both the median household income and gender breakdowns of these counties were similar. So Winona is about in the middle for that. And then we also looked at the age distribution of the counties. So Winona has the lowest percentage of population under 18 years, and then is also among the highest in the population percentage over 65 years old. So just in general, Winona does have a older population than counties of similar size. Yeah.
This is census data, right? So it didn't include students, right? I mean, unless students also.
Correct. This is from the 2016 census. Yeah, so then looking at the forecasted membership, this was done just using so the simple, it's called the ETS algorithm, or the exponential smoothing method forecasting. And this was including the large drop in 2020. And we decided to use the 80% confidence interval just because there's a lot of uncertainty with forecasting. So you just want a larger range of uncertainty. And then here is a separate model also using that basic ETS algorithm to minus COVID, the year 2020 due to COVID. So this predicted the membership in 2022 to be about 4,800. And then it also predicted it to increase into the following year. And then after presenting this to the client, we learned that as of March 2022, the membership was already well over 5,000, and that already surpassed the forecasted totals from the previous model for the entire calendar year. So we decided to do an additional forecasting model. It's called the Holt-Winters model, which weights the most recent time points higher. And since Winona had a large increase in membership in the last 2 years, this would be a good model for this because of the difference in the time series. So here is that Holt-Winters model. And this is using just the 2012 to 2022, excluding 2020, since COVID, it was pretty irrelevant. So this predicts the membership in 2023 to be over 6,000 and then also increase into the following year. And the client was really happy to hear that. So just in conclusion, prior to 2020, Winona had consistent membership numbers from year to year, while other cities did experience a decrease. Winona experienced a large increase in membership in 2021 and also the beginning of 2022. And then based on the final Holt-Winters model, Winona's membership numbers are expected to continue to increase into the next few years. So some of the limitations of this project, there was a large drop in membership numbers due to COVID, so that just made for accurate forecasting more difficult. And then for future projects, you could explore different forecasting models to see what their predictions would be, and then also use similar methods for other YMCAs or other membership-based organizations. That's all I had.
So we can continue.
We can start now. So parity is a concept that most people have a rough understanding of, but don't really have a name or definition for. In layman's terms, parity is just whether or not a number is even or odd, at least when applied to numbers. And as for numbers, it only really has an accepted definition for the integers. And that's what my presentation and my project was about, an exploratory analysis into extending that definition into numbers that aren't integers. So if we're going to extend it into numbers that aren't integers, we should probably look at what it means for numbers that are integers. So the definition is essentially an even number can be written as 2k for some k that's an integer, and an odd number can be written as 2k plus 1 for some integer k. And this essentially means that an even number is divisible by 2 and an odd number is not. Something that most people probably already know. So, and if we are going to extend it into other numbers, we should probably take a quick look at what sets we're going to expand into. First, and for the bulk of the presentation, we'll be looking at the rational numbers, which is just a over b for any a and b that are z, as long as b is not a 0, and that a and b are in their lowest common terms. At least the lowest common terms is how we'll be looking at it in this presentation. And we'll be looking at the real numbers, but the actual concrete definition for the real numbers is a little beyond the scope of this presentation. But we can define the complex numbers, which we will be looking at, which is knowing I, the square root of -1. It's any number a plus bi, where a and b are real numbers. So starting with the rational numbers, we can see that if we try to put in, well, you can probably see if you try to put integers, you're not going to get any fraction that isn't with b equal to 1. But if you try to put rational numbers in there instead, you can see that for any b, we can find some rational number that's 2 times that rational number. So you could say that any rational number is even by that definition. You can also say any rational number is odd by that definition. So that's not exactly helpful. If we want a meaningful definition, we're going to need to look someplace else. So if you consider the fact that for integers, -1 raised to any integer power is going to be 1 if and only if n is even, and -1 if and only if n is odd. And this is the basis for the beginning of our definition for the rational numbers. So we'll see what happens when we try to plug it in with some rational numbers. For a third, we can see that we get -1, so we can call a third odd. And we can see for 2/3, we'll get 1, so we can call it even. But there is a problem that you can probably see, is if you try to do it for a half, you'll end up getting I, which is not 1 or -1. But we're not going to give up with this yet. We just need to look at the function in a different way. And with exponents, a common thing is to normally try to put it into base e. We run into another problem with that because we end up having to find the natural log of -1, which in the real numbers is not defined. But there is a definition for the logarithm in the complex numbers. It is this. It is, we denote it as log log to differentiate it from the natural log, ln. It is the natural log of the magnitude of the complex number plus I times the argument, which I'll get to in a second, plus 2ki pi. The 2ki pi is due to the relationship in the complex world between the exponential function and the trig functions. So if we're talking in the polar form of a complex number, the argument of z is just what that theta is in the polar form, is all it is. It's just the angle that the number makes with the real axis. And the magnitude of z is just the distance from the origin. And it is a multi-valued function, as I said, because angles plus 2 pi are congruent. So you're going to need to account for all of those, and those create different branches of this logarithm. So if we take our original form of the function, apply the log to it, we can see that our function now looks like e to the power of qi pi times the quantity of 1 plus 2k for k in the integers. And since this is multi-valued, we'll actually consider the set of all the values instead of just a specific one. And we can actually plot these in the complex plane. And we can see that there does appear to be a pattern. For a third and 2/3, we actually see that they form these triangles. For a half, it just is 2 points, and for 3 and for any integer, actually, it will just be the point -1 or +1. But you can see that with the fractions that aren't a half and aren't an integer, that they do appear to be a shape. So we will actually make a claim that P of Q is going to form a regular polygon when plotted in the complex plane for any Q, with the aforementioned exceptions. And this is proven by these theorems, because P of Q is going to have exactly B elements in the set for when Q is equal to A over B, and all of the elements are equidistant from the origin, and the two adjacent angles are going to be congruent. So we can see that it does make a regular polygon with the aforementioned exceptions. Also, there is another exception, and that's if you keep the denominator constant on these and vary the numerator, you're actually going to get these star shapes, but they do form, the vertices are still the vertices of a regular polygon. It's just that they're connected in a different order due to how it moves around the unit circle. And do note that each one will contain -1 or +1 or neither. And that is actually the definition that we will settle on for parity. Is parity in the rational numbers. When working Q, we define it first by our function P of Q, and then we can divide it into even, odd, and neutral, or respectively Q1, Q-1, and Q0 to avoid confusion with parity in the integers. Q1 is just all of the rational numbers such that P of that number, there's 1 in the set, and then Q-1 is -1 is in the set, then Q0 is just 1 and -1 is not the set. So looking at this definition, you can see that it might not be a convenient definition to test, just because you would need to generate the set and then see, are these numbers in it? But thankfully, there is another theorem such that given a rational number, A over B is going to be within Q1 if and only if A is even and B is odd. A over B is going to be in Q-1 if and only if A and B are both odd. And A over B are going to be in Q0 if and only if A is odd and B is even. And following from this is another theorem that all three sets are actually disjoint, meaning that we do have a proper division of all of the numbers. And if we want to look and see if some of the arithmetic properties of the numbers are preserved, we can compare addition and multiplication tables for our sets with the actual for the sets for the integers, and we can see that the even does line up with or the Q1 does line up with the even ones for addition and multiplication, and so do the odd. It does get a little more complex when you add in the neutral or the Q0. Most of the time, an interaction with the Q0 number will just result in another Q0 number, except in the case where Q0 and Q0 are added together, or Q0 is multiplied by Q1, you'll actually get, what's the note here, it's Q question mark, because it can actually result in any of the numbers, because the end result will actually be even over even, and you'll have to reduce to figure out what the actual parity of the number is. Okay, moving on from Q, or from the rational numbers, we can look at the reals. There are a couple issues with the reals that make a definition so you can't properly extend it to the reals. That being that our definition relies on A and B for the rational number, and P of X, referring to the real numbers, is not guaranteed to be a finite set. In fact, we prove that if X is irrational, then P of X has infinitely many distinct elements. And for an example, here is pi, some plots of it. We have limited the number of iterations because you can't plot an infinite number of iterations. But notice how comparing them to certain rational values of P of Q, they actually line up very closely. And these rational values that they actually line up very closely to happen to be well-known approximations for pi, like 3/22/7 and 355/113, which is a little less well-known unless you're a math nerd. So this does raise the possibility of, if there was some rational number or some irrational number that had all of the rational, or that had the rational like converging approximations approaching a certain parity, that it could be assigned to the irrational number, but we were unable to find any such number that actually works for, or even define how you would pick the specific rational numbers for that. So, not being able to go further into the real numbers, we instead look at the complex numbers and run into a few issues with that itself. If you look at P of Z or P of A plus BI, you'll see that we get something similar looking, but when you simplify it out, you'll see that there's actually a real number that you're multiplying by or dividing by. It's the same thing, which, so we can just denote that real factor by R, because what's going to happen is that it's just going to be a radius that's going to change as your value of K changes. So you're actually going to either very quickly spiral away from the origin or very quickly spiral into the origin. So there is a way that we can look at this, that we can still look at this. If we recall that P of A plus BI is equal to that, we can actually divide by the magnitude. And that would actually be unchanged for the rational numbers, because we proved that for the rational numbers, it's all magnitude 1. So if you divide by 1, you're going to get the same thing. But if you change it here, we will get the same we will get it. So it's actually P of A plus BI is essentially equal to P of A. But we do run into the same problem with the real numbers with any irrational numbers. So we can define a subset of the complex numbers as Qi, where A plus BI, where any A plus BI in that set, where A and B are within the rational numbers. Essentially, just the complex numbers restricted to the rational numbers. And we can make a definition that looks a lot suspiciously like our definition for the rational numbers, just with the I next to all the Q's and the I next to the P for the sets, but essentially it is the same thing. And you will actually get the same result for the complex numbers as you would if you just took the real part of the complex number. So in summary, we defined parity for the rational numbers. We were unable to find any meaningful definition for the real numbers, And we were able to define parity for a subset of the complex numbers. I personally think that there is more work that can be done in that. I just don't have the tools or know where to go with it yet, but it doesn't feel like a dead end yet. Any questions?